Happy day, everyone. This is Orekoya Olusegun, Physics Mathematics Fundamental on YouTube. Please, before we go into today's topic, do not forget to like, share, subscribe, and click on notification button on my video platform. Thank you so much. Today, we are taking physics, and the topic of today is solution to sound wave in an open pipe. You see, an open pipe that is open at both ends is in this format. When there is a disturbance, standing wave will be set up in the air column. Inside this pipe is the air. This is a pipe. So, and then for the first situation, the wave, the sound wave inside this pipe will be reflected in this format. So this particular point that I have here is called the node. This is the point at which there is zero displacement of the particle of the air inside the pipe. Now, if you look at this particular wave that I have here, each part is a quarter of the total wavelength of a wave. Each part is a quarter. That is 1/4 wavelengths. What I mean by that is that, let me say I have a transverse wave. This is the y and this is the x-axis. If you send a wave like this, from this point to this point is the total wavelength. And if you divide this wave into sections, this particular part of the wave is a quarter of the total wavelength. This is another quarter of the total wavelength. This place is also 1/4 of the total wavelength, and this one is also 1/4 of the total wavelength. Now, if we have a standing wave, that means there will be a reflection of this wave like this. If you compare this diagram to what I have here, we can see that this portion resembles something of this nature, that is a quarter. So we have two of these quarter. So total wavelength that we have here for a pipe of length L, the total wavelength will be 1/4 plus 1/4 times wavelength, equal to the total length of this pipe. If we add a quarter plus a quarter together, we are going to have half. So half of a wavelength is what we have here. What we have here is a node. So we have one. This is called first harmonic. First harmonic. We normally represent with this frequency F1. Now we can equally set another wave in such a way that we are going to have more than a node. Let's say I have a node here and I have another node N there. Here, this portion, the reflection will be shown like this. Here it will be shown like this. Then here we have this wave joining together. So we are having two nodes. In the first case that we have here, we have one node and two antinodes. Antinode is the point of highest displacement of the particle of the medium. Y node is the minimum point of at which the particle of the medium is not displaced. So here now we are having, at this point here, this is the antinode, antinode, antinode. So here we are having three antinodes and two nodes. Now what we have here now is called the second harmonic. So the frequency for the second harmonic is F2. Now let's move down to another scenario of reflection of the sound wave inside this air column. Here we can have this node. Here we are having two of the nodes. Here we can have three nodes here. This node. But before I move further, if you count the total wavelengths that we are going to have here is half wavelength, a quarter plus a quarter. So I have 1/4 plus half wavelength, because this place is half wavelength. If you look at this place, it's half of, from here to here is half, so it resembles this particular place, so half wavelength, then plus another 1/4 wavelength, making the total length of this pipe here. So a quarter plus a quarter is half plus half, that is 1. So that means the whole of this place is 1 wavelength. So I can rewrite this wavelength, this 1 wavelength, as a quarter, 2 times half of it. So I can rewrite this one, what I have here, I can write it like this. When 2 cancel 2, you still have 1 wavelength here. Now, this particular one is called third harmonic. In this third harmonic, I will write F3. We are having 3 notes. So the wave will be like this on each end here. And here, the wave will be in this format. Here too, it will be in this format. If you look at this place very well, here is half wavelength, here is half wavelength, here is a quarter, here is a quarter. So we have a quarter wavelength, half plus half, that is a full wavelength, then plus another here, we have a quarter wavelength. 1/4 wavelength is equal to total length of this pipe. Now, when we add a quarter plus a quarter together, that is a half. Half plus 1, everything will be 1/1 all over 2 wavelength, which is same thing as 3/2 wavelength. Now, if you look at the pattern, this 3/2 wavelength is the total length of the pipe. If you look at the pattern of what I'm having here, for the first harmonic that I have here, I'm having 1/2. Here I'm having 2 of this, and here I'm having 3 of this. So this half of wavelength is common to each of them. So if you look at this first one, for the first harmonic, we have 1/2 of wavelength. For the second harmonic, we have 2/2 of wavelength. For the third harmonic, we have 3/2 of wavelength. So for the nth harmonic, we are going to have nth over 2 of the wavelength, which is the same thing as total length of the pipe. Now, if we remember, the velocity of sound wave is frequency of the sound wave times wavelength. I assume that we understand the fundamental equation of wave. That's why I'm not explaining this under this particular class now. Now, if we make wavelength here instead of the formula, we are going to have, you cross multiply, we're going to have 2L divided by N. When we substitute here, we have V is equal to frequency, nth frequency, times 2L divided by N. So we can rewrite this expression by cross multiplying this N as NV is equal to 2LFN. I prefer rewriting this formula this way, where N is called number of harmonic. So for Fn now, the harmonic will be F1 for when N is 1. When N is 2, we have F2. When N is 3, we have F3, and so on and so forth. Now, because of the coefficient of half wavelength, which is 1, the coefficient of half wavelength here is 2, the coefficient of half wavelength is 3, therefore N take the pattern 1, 2, 3, and so on and so forth. That is for the situation of sound wave in an open pipe. What we have here now, another thing I want us to note is this. F1 is called first harmonic. And I want to also, let us realize something that when we are having Fn, nth harmonic, is same thing as the number of harmonics times the fundamental harmonic. So we need to take note of these two expressions that I have here. Now, I also want to distinguish between between harmonics and overtone of a sound wave. When we have harmonic n to be 1, 2, okay, F harmonic to be 1, 2, 3, 4, and so on and so forth. The overtone, take this format, overtone. Let me take it as this. Take this format. Here we don't have overtone, so I put 0. So overtone start from here, 2, 3, and so on and so forth. So if you look at this place very well, when the harmonic is n, then the overtone, when an harmonic is n, like when n is 2, overtone is 1. When n is 3, overtone is 2. When n is 4, overtone is 3. The n is the number of harmonic. So for here, it will be n minus 1. So if we have nth harmonic, then the overtone will be n minus 1. Take note of this. Now, in my next video, I'm going to solve an exercise relating to sound wave in an open pipe. Please click on the next video. Thank you. Have a nice day. Bye.